Mm-hmm.
You're not just doing 132 divided by 5 since
Yep, since they're both micro. Yeah, you could. All right, so I want you to do 3 on your own as part of your homework. So 3 is for your homework. And we're going to cruise on here. All right. So let's flip this around. Energy stored in a charged capacitor. So if we have energy stored in a charged capacitor, what are the things we need to know? What is it charged at, or what is it stored as? Let's start with that.
electric.
Yep. Electric potential energy, which is what? Voltage, yep. And the reason is you've got different charges on each plate, right? Remember, to get something to flow, think about a battery. To have voltage in a battery, to get the circuit to flow, we have to have a positive and a negative terminal, don't we? It's going to flow from negative to positive, correct? We say from positive to negative, but we know it really is the other way around. Okay, so what do we know? As our voltage goes up, what happens to the charge? The charge goes up, doesn't it? And if the charge goes up, what do we know about stored energy? In other words, the capacitance goes up, doesn't it? That stored energy is the capacitance, guys. This is C. Okay? So now look what it says. It says the stored energy, E, is the amount of work done to force the charge onto the plates. You've got another formula here. V times delta Q. Now, here's the thing. Because the charge, we take the average voltage. If we take the average voltage, guys, I want you to look at this. Average voltage. How do we find the average of something? And divide by? Well, so if we're taking the average voltage of 2 things, that's where that 1/2 comes from. All right? So if we take this 1/2 right here, if we take the delta off of this and the delta off of this, and we take this and plug it in, do you see how we get this formula right here? This formula goes into here. You can't see my, this goes into this and comes out as this formula. So we now have a formula for energy. Energy of the total charge. That is important. Now, the cool thing is this. Since it's Q, V, look at this. Q, V. If we take base and multiply it by height, isn't that an area? So guess what this is equal to? This right here, this stored energy, is this area under a voltage charge graph. That's what it's saying. Area under the voltage charge graph is the total energy. Okay? This area is your total energy. You are. So we've got all right. So now let's look at this guy. It says calculate the energy stored in a 15 microfarad capacitor at 6 volts. How do we do that? Which formula am I going to use? Energy is the key word there. Didn't we just get one of those? Mm-hmm. E equals what? 1/2 what? 1/2 QV, right? Now, here's the problem, though. I don't have Q, do I? So I got to have something with, I got C. So can I relate C and Q and V? What do we know? C equals Q over V. So Q equals what? C times. So instead of this, I could do 1/2 CV times V, couldn't I? Which makes this 1/2 what? One half CV squared. You could do it in 2 steps, or you can do it in 1 step and just plug in the formula. So can we find the energy stored in a 15 microfarad capacitor at 6 volts? E is going to be equal to 1/2 what? 15 times what? 10 to the -6 times 6 squared. What would the units be if it's energy stored? What are the units for energy? Joules, yes. J. It starts with J. Joules. All right. So what do you get?
Didn't do the 1/2.
And -4 joules, okay? So look at number 2 now. It says a 60,000 microfarad capacitor, right, is charged from a 12-volt battery, then discharged through a heater in 0.2 seconds. Calculate the charge and energy before the discharge, and then the power supplied to the heater. So how do we find the energy in the charge? Let's find the charge first. How do we find the, or it doesn't matter. Yeah, how do we find the charge? How do we find Q? Q equals what? CV. So plug in and find those. You get 0.72 coulombs. All right, so how do we find the energy now? Yeah, E equals 1/2 QV. Mm-hmm. 4.32 what? Joules? Now, once the... 4.30 or 4.32? Yeah, joules. Yeah. Now, power. What's the definition of power? Work divided by power is energy over time. Okay? So your power of work is energy, isn't it? Okay? Power is energy over time. That's what you need to know. So this is going to be energy over time. So what was our energy?
4.6.
Okay. What's the time? Yep, 0.2. What? 21.6 what? What are the units for power? Watts. Okay. Look at number 3. It says use the graph to calculate the energy stored. This is a voltage charge. So where is the energy stored going to be? Yep. It's going to be this area down here, isn't it? So we need to find this area. What shape is that? So 1/2 base times what? So what's the base?
40.
And the height is? Okay. So our energy is going to be that area. All right, finish the rest of those up for homework. Huh? Okay then. I said okay then. All right. So, without looking at your notes.
We got camera and we got
List 3 uses of capacitors.
camera and we got what's it called? What's that defibrillator? That thing?
Defibrillator? Yeah.
Defibrillator. And that's a surge.
Surge protector. Good.
What's it called?
A flash?
Pacemaker.
Yes, pacemaker. Okay. What's the capacitance of a capacitor which stores a charge of 2 nanocoulombs on a potential of 4 volts? Oh, what is nano? Yup. It is. Yup. Nano is to the -9. I'm just trying to see if they... I don't have those on there for you. That is a bummer. Milli, micro, nano, pico. Yeah, pico's 10 to the -12. All right. No, that's picante. Pico de gallo, yes. But, so what are you using for your formula? C equals what? Okay. So what'd you get? Farads. Farad. Capacitors are farads. How do we find the energy then? What's the energy stored?
1/2 QV.
Okay. 1/2 QV. So 1/2, 2 times 10 to the -9 times the voltage, which is 4. Yeah, 4 nanojoules, right? All right. So let's talk about discharging of these actual capacitors. How does this actually work? What do they do? And what is the time constant of a capacitor resistor? circuit and how do we increase the time constant. Okay. Remember, these things charge at a certain rate, okay? Or they discharge at a certain rate. And that's what we're going to be looking at here. Ooh, making me crazy. I don't know why these go in sideways. Capacitor discharged through a fixed resistor. That's where you should be. When a capacitor discharges, bang, it's going to discharge somehow, okay? The current does what? It's going to go to zero, steadily decreases to zero. That's this picture right here. It's going to have a sudden discharge, guys. I need you to understand what this is saying up here. There's the graph. Notice that we've got a lot of discharge really fast up front, don't we? Bang. And then it sort of trickles off, and it takes a long time to go to zero. You could almost say that it never actually really totally 100% reaches zero unless you get to infinity, a time of infinity, right? Do you guys see that this is like a logarithmic curve here? Yeah, it's a curve. A lot of that discharge up front is what makes them so dangerous. But why is it doing this? We're going to see it's an exponential decrease. So what happens is you're discharging a potential difference, aren't you? As the potential difference decreases, what happens to the current? As the voltage goes down, what happens to the current? It also decreases, doesn't it? So if the voltage goes down, the current goes down. So once you've got that initial big bang of voltage out, it's going to start slowing down. As a matter of fact, it's sort of like a self-fulfilling prophecy. The voltage goes down a little bit more, so the current goes down a little bit more. The voltage goes down a little bit more, the current goes down a little bit more. Voltage, current, voltage, current, voltage, current. You see what I'm saying? Is why it, all of a sudden you have this huge discharge, this huge amount of voltage, so you get this huge amount of current, and then it just sort of curves off to almost nothing. And the longer you wait, the less it incrementally gets smaller. The voltage incrementally gets smaller, so the current incrementally gets smaller. All right, over time. Now, this is your circuit right here. See what I mean about the double plates? And see what this is? This is a switch. You've got a switch there that's going to switch, like right here maybe. When that's open, the capacitor's charging. When it closes, now all of a sudden you've got a completed circuit and it can flow. The voltage can flow, can't it? All that charge can release. All right? So you got this incremental decrease across of the voltage across the plates. All right. Does everybody understand why it happens that way? So let's look at what we see here. We've got three different incremental curves or exponential curves we're looking at. First one's the first one we looked at here, guys. This is current versus time. This is the one we saw, isn't it? But now look at charge versus time. Think about it. If the current is decreasing, that means it's not pushing as much charge, is it? Remember, the current's the thing that pushes the charge, right? So if the charge isn't being pushed, then it goes down over time. Right? It's the same curve. And then look at the voltage. If the current and the charge are both incrementally going down, the voltage is also incrementally going down. It's the same curve for all three. That's what's happening. All right? So you got a high force right here, because remember, that's what your current is. So if you wanted to make some notes and think about it this way, this is a high force pushing charge. And now this is a low force. Pushing charge. Okay? So we're not driving our charges hard. Right? Same thing that happens every time. Big thing I want you to notice is that all three of those are the same. They all act the exact same way. Okay? So the fractional drop in the charge is the same for any time interval. All right? And that's this right here. That's what this guy is saying. That fractional drop is the same no matter what, over any time interval. Now, what exactly does that mean? what is time interval? What is our time constant? Hang on. Unlock this and rotate. Let's look at this guy. Is this the next one you have? That's what I thought. All right, so we got a microfarad, 40 microfarad. Mine are out of order. Cool. I knew I'd gotten them out of order. I just couldn't tell where. All right. So it says, what's the charge be stored before it discharges? So how do we figure out what's built up? What formula are we going to be using? Okay. So C equals Q over V. And we're looking for charge, so we're going to do Q equals what? C times V. So can we find that? Come on. Stay focused. You were not. You zoned out again. We'll quit it. You're not zoned in what you're supposed to be zoned into. Actually, I think I have yours out of order. Mine were in order. I think I put yours out of order. We're going to go back and talk about a couple things here in a minute. Talk about that time constant. Because now look what it says in part B. What does it say? What's the time constant? Time constant is when T equals tau. This guy right here, time constant, is that Greek letter tau. Tau. T-A-U. Tau. Tau is equal to R times C. The resistance in the circuit times the capacitance. Okay? Now, what does that tau time constant mean? Okay? When we talk about a time constant, it depends on whether or not it's discharging or charging. All right? So, let me see. Do I have it on here? Charging capacitor? Yeah, right here. If we are charging a capacitor, tau, which is this guy right here, amount of time it takes for it to be 37% away from full value. So if we're charging tau, and this is discharging, this is charging. No, hang on. Yeah. 37% away from full value. That would be like here. Here. Yeah. This is discharging. I got the wrong picture on here. All right. So what we know is that charge, the total charge, Q, from full value, what we're talking about is Q being 63% of full. Okay? Does that make sense? If it's charging, okay? If it's discharging, it's the exact opposite. So this is for charging. For discharging, it's going to be Q is 0.37. 37% away from being fully discharged. It's that same time constant, though. It's that same idea of 37%. So, I want you to look at this picture, though. This is discharging, isn't it? We said we want to know 37% away from being fully discharged, right? 37% away from being fully discharged. If fully charged is here, that would be approximately a little more than a third of the way, wouldn't it? So if we're talking about it being up here, a third of the way would be, well, actually, I think it's more like here. This really is kind of, there's half, so this really is closer to a third, isn't it? A little more than a third? And how we figure out what that time is we full it, because remember, this is potential difference. This is voltage over what? Time. This would be time here. We follow this over to the curve, and then we follow it down and figure out what that time is, okay? And whatever that time is tau, okay? Now, for charging, it's the opposite. For charge, are you serious? Can't ever get through anything with y'all. Well, we'll finish up. We'll finish up capacitors next time. We got to do capacitors in series and capacitors in parallel. Finish up your circuits stuff, okay? Finish the problems that we have in here already, okay? And then finish up your additional circuits practice worksheet. I did. I believe I gave you 3. We'll finish this next time.